Okay. 5 and a bit in the afternoon, Math 2504, 2024. Welcome to Unit 6. It's a great pleasure to introduce Dr. Paul Verbeek. Paul's been at UQ already a couple of years. When we first introduced him in this course, he was fresh off the boat or the plane or maybe the quarantine because he migrated from Canada.
Oh, shit. I muted Yanni. Yanni, I muted you by accident, right? He's not in here.
Oh, there I am. Okay.
Sorry. Go ahead. Sorry. Yeah, keep going.
Well, I was muted for the last couple of seconds, but that
Yeah.
was all the good things about Paul. Let me
I
now
see. Yeah,
all
now
the
you
bad
can just
things.
move on to the bad stuff, right?
No, I'm joking. Look, you'll really enjoy, I hope, these 6 lecture hours with Paul Verbeek. It's kind of intense, obviously. Everybody's working towards project 2. But the thing is that we've got an expert in computer algebra systems. And Paul is unique in the sense that he is a teaching-focused academic in the CSSE or EECS or ITEE or
Right.
that department. But he's actually an exceptional mathematician. So I hope you enjoy his lectures, and also make sure to use his time to ask as many questions as you can about project 1. Thanks a lot, Paul Verbeek. Okay.
Thank you, Dr. Yanni. I'll see you later.
Bye.
Now I may mute you. All right. Let's get some. Right. Okie dokie. Let's get rolling. We're not doing all 73 of these slides, don't worry. Turn down the microphones a bit. Yeah. More people. 2, 4, 6, 8. We almost doubled. Okay, hello everyone. Welcome to my module in 2504. As Yanni said, I've been doing this for about 4 years now. I hope some of you find it fun. Why am I here? Well, about me. So I have a PhD. I'm from Canada. Don't hold it against me. I have a PhD in computer science from the University of Western Ontario. That's in London, Ontario. And I did my PhD in computational algebraic geometry. Before that, I was in Vancouver at a university called Simon Fraser University studying pure mathematics. I was also doing computer algebra. So this is very strange that I have a computer science PhD, but like before that, my entire pathway was through pure mathematics. So at McMaster University, that's my alma mater for my undergraduate, that's in Hamilton, where I was just doing sort of algebra and computer science. Like we didn't really have these dual diplomas at the time. You just took whatever you wanted, right? So somewhat like one of my objectives here is to prove to some of you pure mathematicians and perhaps convince you that you can be deployed into computer science for developing tools for other mathematicians, right? Like mathematicians had to invent the calculator for other mathematicians to use. Symbolic computation is effectively like a higher order calculator, one where we're going to be computing with symbols rather than numbers. And that's like very, very useful for other mathematicians. Now the problem, you need to understand both disciplines in order to work in the discipline. Okay, that's perfect. That is perfect, right? I think the projector detected it on the computer science and then decided to not work. That's always the joke. I have no idea what has happened. If everyone here would just come stand behind me, then we'll sort this. Okay. I don't know. Okay. I hope that doesn't keep happening. Because if it does, I may have to switch computers. Okay, we'll see. Where was I? Okay, so you need to be a mathematician in order to understand the math. You need to be a computer engineer in order to implement all of that math properly. And the other thing that I do in my discipline is we're not simply implementing stuff. Like you've been learning algorithms, like instructions to solve problems. given to you at some type of high-level language like English, and then we've asked you to implement it. That's one version of programming. But there's another, like, who invented the algorithm in the first place? Right? There's like the whole category of people who have to be algorithm designers, who sort of like don't care about the computer, but care about the problem at hand and actually devising a ordered set of instructions that will solve that problem. Now let's see. Let me show you the Maple system that I worked in and did most of my all of my dissertation is effectively in this computer algebra system, this commercial computer algebra system. This company in part paid me, like paid for my scholarship when I was in school. They would kill me if I ever showed Maple like this to actual people trying to sell this to. Like marketing would be furious, right? This is the non-fancy, I've reverted this back to the 1980s style version of Maple because it's what I'm used to. But you should know, like in its natural state, it looks a lot more almost like a living scientific paper. It's a lot more fancy, but I prefer this, right? Because I actually have to engineer in here, so I hate the 2D input. Okay, so foremost, the most important sort of object of computer algebra is that of the polynomial. And that's because we need to exactly represent all numbers. So what are all numbers? Okay, so can MATLAB, for instance, which is a numerical system, can it represent integers? All of them? Not really, some of them. Can it represent rationals? Some of them, right? That's what the floating point numbers are, like a sort of a finite collection of some of the rationals. Can it do complex numbers? Kind of, only because it's sort of isomorphic to a vector and it can work with vectors. Can it do a number like the square root of 2? Or a third? Right? Like these are pretty big deficiencies in a system that you're trying to give to mathematicians. It's sort of like, I would like to do computations exactly. Oh, do you intend on using fractions? Yes. Oh, sorry, like not for you. So what we had to do is develop a system where we're able to use most of the numbers that mathematicians are used to using, like a third and the square root of 2. So we don't really, at the basis of this system, have numbers living there. The most important object is that of the polynomial. Why? So what is the square root of 2? How is that described? Pardon me? It's the root of x squared minus 2, right? X squared minus 2 is what we call the minimum polynomial for the root of 2. Suppose then, what is the category of those numbers called? Those numbers that are roots of polynomials with integer coefficients. Algebraic numbers, right? So, okay, so we don't really have 1 in this system. We have the root of x minus 1. We don't really have the square root of 2. Like what is even that? It's not a number, it's a property, right? So we have x squared minus 2. Okay, so we have at the bottom of this polynomial, so I'll show you that we can work with them, right? So here's the polynomial. Come on, don't die on me now. Okay, right? And the first thing that you see is we have this sort of structured output. You're going to have to do this in your project, right? Right now, the polynomials are printing out in a very simplified sort of 1D fashion. We'd like for you to utilize Unicode to make them look a little bit prettier. It's a little bit harder than you may think because there's a bunch of weird edge cases. Like we don't ever write 1 times x to the power of 1, right? You write x. We don't put a plus symbol in front of that 4, but you do put a negation there if there's a negative there. We don't write zeros for 0 coefficients, right? So anyways, we can have it look nice like this. Here's another random polynomial. And I can do things like form their quotients, right? And it has structured output like this. I can expand them as much as I want. And here's the magic, right? Here's this magic simplify h. What do you think simplify h is going to do in this instance? I hate this command for this reason. Can someone give me a canonical definition for what simplification should mean? Well, it's going to say that it's factorization, but who's to say that's simpler than the thing that came beforehand, right? So I don't like this notion of expanding and simplifying. Perhaps here I would prefer to say expand factor, right? And factor is what I'm going to be teaching you how to do. Does anyone know how to like Well, first of all, you know how to factor, right? Do you know where that ends, the closed forms? So you can probably factor a quadratic polynomial. Why? Because of the quadratic equation, right? We know how all of those look. Same is true for cubics and quartics. What about quintics? People are shaking their heads. Some people here have taken Galois theory. Okay, so you know, or I'm telling you, we don't have solutions for quintic equations or beyond. And it's not that we can't find them, it's that they provably do not exist, right? There is no closed form for quintics and above. So the question becomes, how do we factor quartics or quintics and beyond? And I'm going to show you a very amazing algorithm that does this. It's quite simple, but extremely powerful. That's why I chose it as the topic. But I also want to sort of demonstrate to you that it's factoring is kind of important. What's factoring equivalent to, kind of? That's not the answer I'm looking for. What can you read off of this that you can't read off of that? Its roots. Its roots are much more discernible from this factorization than from this expansion, right? So in some sense, factorization is sort of equivalent to solving something. And I shouldn't really have to explain why solving things is important, but it is, right? For more or less all of science. Those of you who took Comp 3400 with me know that it's like stupid easy to explain to the computer how to take derivatives of stuff. Right? Because there's maybe like 4 rules that you have to tell it, right? The sum of the derivatives is equal to the derivatives of the sum. You have to tell it product rule. You have to give it, a to the x to the n. Its derivative is an times x to the n minus 1. And once you explain it, you can do stuff like this, right? And get the derivative quite quickly. If we look up here at h, we can take integrals of this, but that's not really that impressive, right? Because this is just a polynomial. Any undergraduate student should be able to take the integral of that just by increasing the exponent and multiplying through by the right coefficient. But what about stuff like f over g? Who can integrate this? Where would you start? Huh? Partial fractions, and then factorizing and a bunch of stuff, right? But who cares? Right? I don't want to integrate by hand. In fact, most of us don't integrate by hand. We integrate by using a computer. Some of you have taken a numerical analysis course. Well, one of the things that's very an important topic in numerical analysis is that of numerically integrating stuff. And why is that a tool at our disposal? Like, why should it, like, if I said go home and numerically integrate something, would you know how to do that? Do you remember what a Riemann sum is? Right, that is basically the numerical approximation of an integral. Just choose an arbitrary number of squares. Remember, you got a curve, and then under this curve, you draw rectangles, and then you make the width of those rectangles arbitrarily small, and in its limit, that's the definition of the integral. So any of those summands are going to be some approximation of the integral, but that's not what we do in symbolic computation, right? I'm saying we have to have the exact solution. So how does that look like in this system? Okay, it looks like this, and everyone may be saying, well, how the hell is that an integral of something, and why is that useful? But it is useful to mathematicians. So here is like the whole part of the partial fraction expansion. So that's sort of like the easy part. This is the hard part. And how do we read this? Well, I'm saying the integral is equal to this plus the sum of these terms, summands, where this r is a root of this polynomial, right? It's some fifth, it's an algebraic number with it's some fifth root of something, right? Well, what is it? Well, it's that. That's it. That's the number. It's the root of that. I can't give it to you because it's not a number. It's a number which is only defined by a property. That property. Right, so this is about as far as we can take the integration symbolically. If you want to go further, fine, and pick a numerical technique like Newton's iteration and go get it. So I'm not saying this is the be-all end-all because, yeah, there's like lots of instances in science where this would be insufficient, but symbolics and numerics have to play in concert with one another. Like you can't numerically solve something until you're given the thing to numerically solve. Right? They need to know, oh, we're searching for roots of here. Is root finding even simple once I give you that polynomial? Sometimes, like, it depends how ill-conditioned the problem is. Let's hope roots aren't very close to one another. Let's hope roots aren't repeated, because then we won't know if we found them all. So like, there's a lot of things that can go wrong when you're working numerically that are evident when you're working symbolically, right? So I enjoy working symbolically. Okay, so I'm just going to show you some of the higher order language features before getting into some of the stuff that I personally worked on, because I just want to show you that, you know, this does all the fancy stuff. Like, look, you can plot all of those things, no problem, and export very nice what is it called? Print quality illustrations if you want. We can plot in 3D if you wish, right? It has all those shaders and all that interesting stuff. We're free to change the coordinate systems that we want to plot in, right? So here's a cool 3D sort of shell that's plotted in, what is it, a spherical coordinate system. This is sort of a spiral that goes infinitely into itself. Let's study this equation right here. I think it has a name, maybe Ojika. I forget. Some of these systems are so widely used that they get their own names, but it's the sum of cubes, like x cubed plus y cubed plus z cubed plus 1 is equal to x plus y plus z plus 1 all cubed. Okay, so that's an expression which I want to plot. And what is going to be interesting about this plot? Well, we're gonna see a surface, but the surface is going to cross over itself somehow. And those crossovers, those intersection points, is the solutions of that system. And like, so this is what I'm mostly interested in computer algebra, is solving systems of polynomials. Now I'm going to plot this, but what's weird about this plot? It is 3D, actually. Yeah. Well, normally when we plot something, don't we have to plot a function? Is this a function? No, usually when we plot something, one of the variables has to be linear, right? Z is equal to this function of x and y, and we have some domain, and we just say, oh, and thus this part of the domain, this is the elevation given by Z. We don't have any linear term here. So even the fact that we can plot implicitly is really cool. I love this command, right? Because it's just like, yeah, this is it, right? That's that system up there. And we're very interested, or at least I am very interested in studying them, especially the common places where they intersect. Like, the real name of the research area I'm from is computational algebraic geometry. Because if you think about, like, what do we do mostly in math? Like, it really boils down, or at least system solving, boils down to manipulating shapes in space. Right? But how do you explain something like a circle to a computer? A computer is a discrete actor. Right? You need to have some codification of all the shapes that you want to do. Well, what is the codification? Algebra, right? Algebra can, in a discrete fashion, allow you to define continuous things. So that's pretty cool. And then we have to be in this sort of algebra geometry correspondence, right? There's like a bunch of theorems that allow us to move from one domain to the other. And it's weird because you lose and gain stuff as you jump from algebra to geometry and geometry to algebra, but it's a really neat interplay. So I love this sort of implicit 3D plot, because you can generate these like really neat sort of pictures in space. Not only that, we can animate stuff. So if you've ever seen the Bessel function, there it is. There's just something which I want to do, constrain the scale. So this is the function which sort of simulates what happens if you hit a drum. Okay, you ready? Drum. All right, but we could do stuff like this. And obviously you can make much more interesting things with sliders and all the, right? So search Maple, like full features on your computer, and marketing will have something very nice. I just wanted to mention the graph theory package, because when I was a master's student, the individual beside me was building this package, and he was very bright. I think one of the feathers in our cap is how well this works. So we all know what a mathematical graph is. It's effectively just, well, give me a bunch of tuples, right? That's a graph, right? Or if you give me the tuple 1, 2, I know that there's some agent or node called 1, which is connected to another thing called node 2. And then what we normally like to do is draw these in some fashion. So here's a graph. This is a undirected, unweighted graph with 9 vertices, 15 edges, and 2 self-loops. It's a random graph that I somehow collected. Now, if we wanted to draw this and look at it, what is the most obvious way of doing so? I asked to go home and program something so I could look at this graph, right? There's one obvious thing to do in this setting. Yeah. Yeah, draw 15 gone and then draw the interior of that. So that's obviously not going to be ideal, but there you go. Have any of you taken graph theory? Yeah. So do you guys draw graphs like this? No, of course not. Like, because we like to draw spatially pleasing graphs. So this fellow had a neat idea. He says, hey, what if we consider all of those edges springs? Right? And we just like attach everything with springs, and then we give the graph a good shake. And then we let that graph come to like a stable point. That should stabilize to something prettier looking. Okay, so it looks like this. Right? Or like, this, or like this, right? Because you can keep shaking it and letting it stabilize to something that you want. And then eventually you should be able to generate a picture of a graph that, I don't know, like you would want to use in a paper or something like that. Okay, so that's something cool that my neighbor did. So now I'll tell you what I did, because it's going to be the launching point for talking about, your project effectively. So here is a polynomial. Let's just forget the fact that like I expanded it from something. So pretend you don't know the factorization of this. So this is our starting point. Again, like what should it mean to solve f in this case? Like, what do you think is going to happen if I hit enter? Like, what would people want, right, when I would say solve this? Roots. Okay, but what if the roots aren't numbers? Or what if the roots are algebraic? What do I do then? Right? I think what you're trying to say is factor, like present it in a factored form, and you would be correct, right? So what are you thinking? No, that's not possible. Something. Okay, cool. I'll blame the machine for it thinking that long. That was surprising. So you said factor, which was correct. I'll just do this so we can look at both at the same time, right? Because the reason that Maple was able to do this is because it's able to do this, right? So the first point is factoring isn't just some game that we're playing. Factoring is solving polynomial systems, right? Which is of critical importance to science. Are these the roots of these? Let's check. Do we have 1? Do we have square root of 3? Do we have the minus square root of 3? Do we have all of the 3 third roots of 5? There you go, right? So Maple just knows that, oh, when you have simple algebraic numbers like this, or at least some of the algebraic numbers, have special notation using this radical symbol, but effectively it's the same. It's the same, right? So if I show you how to factor, I've shown you how to solve polynomials beyond quartics, right? Which you should have known is impossible. Can you trisect any angle with a straight edge and ruler? Do you know what that even means? Geez, we're really losing all of the classic math. You know that the thing that in your compass set that's sharp, right? That draws circles. If I give you that and I give you a straight edge, that is just, I swear that guy's just going back and forth to troll me. If I give you a ruler with no gradations on it, the question becomes, what angles can you draw with a straight edge and a compass? And you can draw a 90-degree angle. You can take an angle, you can cut in half. So the question becomes, can you take any angles and cut it into 3? And the answer is no. And it's related to the fact that you can't solve quintics, believe it or not. So Galois theory also is a result on what angles are constructible with straight edge and ruler. All of you should take a Galois theory course. It's quite. Do you know about Galois, like the mathematician? Like, do you know what he did that was quite stupid, right? Okay, so like I have 5 minutes. Okay. Well, first of all, he was like sort of a political activist, and he died quite young. So there's like a joke that like sadly Galois learned that not all problems are solvable by radicals. Okay, so that's the one joke. But the real story is that he fell in love with his best friend's partner, Coquette. And so he did the sensible thing and challenged his friend to a duel to the death, right, over this lady. But they were best friends, so they couldn't actually stomach dueling one another. So the duel was like a Hamilton-style duel, like think 10 duel commandment type of thing, where they're going to have pistols. So they said, look, load one of the pistols and not the other, and we'll just stand in front of each other and fire to each other's stomachs. We'll let the universe decide which one of us gets to stay around. So what happens the day before a duel? Because you don't do the duel the same day. It happens like the next day. So you can have a real good sleep about what you're going to do. Yeah. So he's sequestered, which means you're sort of jailed, so you can't run away like a coward. And in this sequestering, he realized, yeah, I'm going to die tomorrow. Like this was an exceedingly dumb thing for me to do. So he wrote down everything he knew about math on like 2 pieces of paper in his jail cell. And then mathematicians spent like the next 2 centuries like unpacking that paper and developing Galois theory effectively. So it's just what could we had more if Galois stuck around? Now it begs the question, what was the profession of the other fellow who survived? Like, who did the universe choose to keep us with? Does anyone know the profession of the guy who survived? Because it's ridiculous. Do you know at Christmas how we like pull apart those like party things? Yeah, he made those. Like that was his profession, was like making those Christmas crackers. But who knows? Like maybe there's some butterfly. Maybe that was some canon moment in our timeline. You don't want to screw with these things. Okay, anyways, so that's highly related to us factoring, and factoring is the same thing as solving, right? So beyond that, though, what I want to do is solve systems of polynomials, not just one polynomial. What happens if I want to work with a bunch of polynomials? I'm sure you've all taken linear algebra, so you've done some system solving on things that are flat, right? If I give you a bunch of hyperplanes, you can tell me where those hyperplanes coexist. Now, the natural question becomes, does Gaussian elimination generalize? The answer is yes. I had this question immediately when I learned it, and it took me maybe 15 years to get the answer. I had to go to graduate school to get the answer to that question, because it's not simple math, it's high-powered math. Okay, so if I give you another G, right? I give you G and I give you F, and now the question becomes, what are the solutions of F and G as a system? What are their shared roots? How can I get that? Pardon me? So like one thing I can do is just factor G and then like pull out the things that look common. But isn't that the GCD operation? Right? The greatest common divisor is going to pull out what roots are common to F and G. So if I can do GCDs and I can do factoring, I can solve systems of polynomials now, right? Which is pretty cool, right? We're going beyond all of this linear. So if I solve this, what is Maple reporting? Oh, it's the root of z squared minus 3. It's plus minus the cubed root of 3, which are the common solutions to F and G, right? And this is all the univariate setting, and all of your project is going to be done in the univariate setting. But obviously, we can take this to multivariates, which is the last thing I'll do, and then we'll move on to actually talking about course material. So here's a system of polynomials in 3 variables, x, y, and z. This is how they look like, right? This system is called Ojika, right? So you see 3 surfaces here, and they're like overlapping in space. And the question becomes, what is their overlap? Okay. Think about how MATLAB it's hopeless to be deployed on this problem. If I give you a sphere and I cut it with a plane, what do you expect the answer to be? Circle. Can MATLAB say circle? No, it can't. What's the best that MATLAB can do in that setting? Yeah, it can give you a parametric equation that says, you give me t, I'll give you one of the roots along the circle, but it can't properly report back the equation for a circle, which is what Maple would do, because we don't distinguish between numbers and equations. Right? We're saying your solutions is this circle. The circle is the solution. If you want points along that circle, that's weird to us pure mathematicians, but we can give it to you if you want using numerical methods. Okay, so how then do I get the solutions off of that? Well, the most sort of the first method for doing so is called Grobner-Basie's or Buchberger's algorithm. Now, Buchberger is an Austrian. He's alive, and he semi-recently won an award for being like the most important Austrian, because this development of this Buchberger's algorithm in the 70s was really, really important, right? It was like the new Gaussian elimination, right? So like imagine you invented Gaussian elimination, It's pretty crazy. Pardon me? Imagine you were a Gauss. Yes. Anyways, so here is a system of equations that have the same roots as f's. Okay, so you all worked with vector spaces, I'm sure. Okay, so I can give you a set of vectors and a different set of vectors, and I can ask, are these generating the same vector space? And you have various methods of doing this. One of them is to find a standard basis for both and ask if they're the same. What was that algorithm called? Graham-Schmidt orthogonalization, right? So there is an analog to this when working with sets of polynomials. But we don't have vector spaces. We have these things called ideals. Does anyone know what an ideal is? Okay, so if I give you a set of vectors, its vector space is formed by making linear combinations of those vectors. That is to say, you can sum the vectors and you can scale them by constants. In an ideal, you have a set of polynomials, and I say you can generate new polynomials by summing them, and you can scale them by other polynomials. Right? So if I have sort of the generating set x squared, you're never going to have a linear polynomial because you just can't get it, right? Everything has to be multiplied by x squared. Okay, so we're not going to be talking about ideals, but what Grosvenor basis does is this is effectively the Graham-Schmidt orthogonalization for polynomial ideals. Okay, two ideals are equivalent if and only if their Grosvenor basis, when we use the lexical ordering, monomial ordering, are the same. Now, what the other thing interesting, okay, so what I'm saying is that this Grosvenor basis has the same roots as that f's, but let's look at what is actually in there. Okay, so these are the polynomials in there. Do you notice anything about it that is different than the original starting set of polynomials? I'll give you a hint. So the top polynomial has how many variables? That is to say, we've eliminated two variables from it. The one underneath are in what? Y and Z. And the last one is in X and Y and Z. What does this mean? Oh, pull a root off of this, substitute it into these two, solve those two, get a Y root, sub it into here, get X. So this is sort of like this upper triangular form from Gaussian elimination, right? Really, in Gaussian elimination, that is the strategy. You need to isolate the variables one at a time. So are you satisfied with this being a solution? Can you give me a point in the solution set? Okay, so maybe like we need to go further than this. Okay, so my laboratory, ORCA, the Ontario Research Center for Computer Algebra, was largely concerned with working in these things called regular chains, which is sort of Gaussian elimination, Buchberger's algorithm plus factoring at the same time, right? Because I'm going to solve the same problem. So I'm saying I want to work in a polynomial ring of X, Y, and Z. Here's my F's, it's this Ojika system. And we have this triangularized routine, right? Which is effectively going to say, try to produce well, I'll show you. It's better than saying, okay, so I'm going to do this. And this is what it spits out. Is this a nice representation of the solution sets for that? Right? Look, you can see, oh, here's one of them, 0, 0, 1. Here's another one, 0, 1, 0. Here's another one, 1, 0, 0. And the last one is, well, one of the square roots of 2. Then y is the negation of that and x is the negation of that. But it's all of them. Have we found all of them? Okay, so here's the original system. This has total degree 2, total degree 2, total degree 2. What is the most amount of roots that we can expect to find in this system? You're adding. You should be multiplying. 8. It's 2 times 2 times. Let's think of a different problem. Parabola, that's degree 2. Line, that's degree 1. How many solutions do you expect in that setting? 2. 2 times 1, not 2 plus 1, which would have been 3. Right. So what remains here is to confirm that we've actually found all of the solutions. That's where I came in. Okay, so that was my task. Oh, so first of all, let me just hit this button. This is a big feather in our cap. most people buy Maple in order to call this function solve. And what solve does is call the regular chains package. So we're like quite happy about that, right? Because the main drive of the system is solving, and they're using what is in effect the technologies coming out of the laboratory that I used to work at. So you can see it's just taking these sets and sort of describing them a little bit sort of differently. They're just explicitly saying, get one of the roots of this polynomial, and then you can carry it up the chain. Okay, so for me, what they said was, look, we need to actually confirm that when we found all of these solutions, that we found all of the solutions. So there is a statement. Does anyone heard the term intersection multiplicity? So sometimes, okay, so I want to say something like the weighted sum of roots in this system is equal to the product of the total degrees of the system. What's the weight? Well, the weight is something called the intersection multiplicity. So on the parabola line example, the intersection multiplicity of a line going through a parabola, like the normal intersection, 1. Each one counts once. What about the tangent intersections? That will count twice, right? Because it's an intersection that happens at a tangent. And sort of like that's basically it, right? You want to count it's the dimension of the tangent space at the point of intersection. If that intersection is happening tangentially, that needs to be counted. I had 6 years to figure it out, and I managed to implement this library, Algebraic Geometry Tools, which takes our triangularized routine and just adds the secondary part, triangularize it, but also give me the multiplicity. Let it do a little bit of thinking. So we get something like, you see these numbers? 6 years of my life went into producing these numbers, but it's saying these 2 roots here count once. And actually, these roots here were happening at tangents, so we should count them twice. So 2 roots here, 4, 6, 8. Yeah, you found them all. These are all the solutions. Right, so that's really important. I've given you solutions to the system that you can immediately confirm are solutions because you just evaluate your polynomials at that. That's free, effectively. And now you're guaranteed to have found them all. So what I have to impress upon you here is that I wasn't given a paper and they said, implement this. They said, here's a number. We know it exists. There's definitions for it. How do we compute it? Right, so there's a whole field called the constructional mathematics. And what we do in constructional mathematics is actually write constructional proofs, because what is a constructional proof? It's an algorithm for producing an answer to something that you're looking for. And we'll talk a lot about that today. So I used to work in a laboratory called the CECM, the Center for Experimental and Constructional Mathematics. And I'll talk more as soon as I get the screen back. Perfect. Okay, so that's enough of that. That's enough of that. So now let's start talking about this as well. Don't save. All right, so the whole point of that is some of your pre-mathematicians who enjoy using a computer, there's a space for you, right, to develop tools for other mathematicians to use, which do get used. You'd be surprised how much computers can get used at sort of these higher levels of, like, none of us want to actually be integrating in real life or doing any of the linear algebra that you have learned how to do. Where no one is doing by hand Gram-Schmidt orthogonalizations, right, in the university ivory towers, except for you guys, right? We've invented it to punish undergraduate students, that in calculus. Okay, so we're going to start now is talking about computer algebra, because I need to teach you like how to build it. And we need to think more critically about things that you've been doing that we've been taking for granted. Like you've been working with polynomials and you've been sort of factoring them and dividing them and multiplying them. But we need to speak more precisely about what some of these operations mean and the environments where these things are actually going to be well defined. So I want to give really rigorous definitions to polynomial arithmetic. Do the terms integral domain, Euclidean domain, group, ring, are these meaningful at all to some of you? Don't worry too much. So I'm going to go through some stuff, but you should know that there's also videos that we paid another lecturer to do for this course. where he talks at much greater length about some of the basic algebra and ring theory that I'm going to be going through that may be too quick. But honestly, it's not so important that you understand everything perfectly. Like, we're not going to be asking you to do any proofs or anything like that. As long as you sort of get the vibe of what's going on and you understand enough of the terminology to not be totally lost when I'm explaining the factoring algorithm, it should be fine. And me and Yanni are going to be around for a lot of consultations. So, and like, truth be told, we actually took the project and made it a lot simpler this year because you have your shortened time frame this time to do it. So, but it should be fine. Certainly pretty printing, you should just sort of jump in and give it a go. Okay, so first of all, I just want to acknowledge that sort of these were notes that I studied from when I was like an undergraduate like you, or sorry, graduate student. So I adapted them for this course. So they're based on Dr. Michael Monaghan's course. So if there's mistakes in this, it's probably my fault, not his fault. Okay. And Yanni wrote the Julia code. The other thing I have to sort of acknowledge is I don't really use Julia professionally like Yanni or any of the other people teaching you. I dabble in it. I'm going to know enough maybe to help you, but I don't really know it down to its very, very core. So that's not, sorry. I've been trying to learn it. Okay. So there's the slides. They're online if you want to look at them. You just have to run all of these things. So I saw a question on the EdStem about this package instantiate taking a long time. That's normal. It will only take a long time once, because what it's doing, it's downloading a bunch of packages and some of them may be big. Julia has many things. It's not a small footprint, right? Okay, so let's just start talking about symbolic computation and all the other things that we're going to need. Is this large enough for everyone to read? Yes. Okay. So what does it mean? Okay, so we need to compute symbolically, which means we're not going to be able to use floats. Floats are off the table because the floats are effectively just rational numbers, but some of them, right? And if we want to work exactly, what I'm saying is like we need the integers, all of them, all of the integers. We need to be able to work with rational numbers with arbitrary number of digits in them. So like floats are off the table, period. We're not even going to talk about them. Because root 2 has to be equal to the square root of 2 and not some approximation of the square root of 2, right? If we're off by what happens, okay, so basically a number which is a float is effectively an interval. I'm saying the solution falls somewhere in here. What happens if you take an interval and you add another interval to it? Interval gets wider, okay? So when you're working with floats, adding introduces error. When you're doing Gaussian elimination, what are you doing? Adding a lot. Right? So most of numerical analysis is effectively just trying to avoid adding in Gaussian elimination, because there's no point in saying like, what's the person's height? Oh, it's like 1.63 at 4581 meters plus minus a kilometer. It's like, oh, okay, thanks for that. Like that's totally useless. So we're not going to have to worry about any of this type of floating point error because we are working exactly. There is no error to propagate through our algorithms. There is a secondary problem of the numbers that we use getting huge, but we have a way of mitigating that through something called Chinese remaindering theorem. Does anyone know about the Chinese remaindering theorem? We'll get to that. In effect, it means that we can solve this problem using some, not all numbers. And we can solve it a bunch of times, then recombine it to get the solution over all of the numbers. So we sort of got the expression swell problem sorted. So our interest is in performing exact computation over rings with efficient algorithms. In particular, we're going to be working with the integers, right? 0, -1, 1, -2, 2, and so on. And in particular, I want to work with this ring. And most of the energy of today's lecture is going to be establishing this ring and its qualities and capabilities and what we will and will not be able to do with it. So the ring of polynomials is formed by taking finite sums of terms, and terms are broken into coefficient monomial pairings. So it's you know, something like 3x squared minus x plus 1. That counts as a polynomial. And clearly we can do things like add them together, multiply them together. Can we divide them? Kind of. Can we get GCDs of them? Maybe. So let's see. Okay, so here's the preliminaries. It's first necessary to establish a bunch of terminology, so we're all on the same page when we're talking about this stuff. So let this Blackboard N denote the natural numbers, 0, 1, 2. Who's already pissed at me? Who thinks that the natural should start at 1? Good, because you'd be wrong. You'd be wrong, right? Well, there's a cultural difference at hand here. Some people start naturals at once. Some people started at 0. We start from 0, mostly because that's the way it has to be. Like that, I wouldn't know why we'd exclude it. Julia is not a 0 index language, though. Yes, or it is. I forget. 1 index language. Okay, that's unfortunate. Okay, so Blackboard N is the natural numbers, Blackboard Z is the integers, and we'll use this Blackboard P to denote the set of all of the odd primes. Just go ahead and exclude 2, because the fact that 2 is an even prime, that screws up things usually, and it's also too small to be useful anyways. So we're going to start with a definition of a ring. So what is a ring? Well, more generically, in math, you can take any set of anything, and you can imbue that set with operations like addition or multiplication, right? So if you have a set and you're able to imbue it with addition, so that addition is closed, that is to say, if you add 2 elements in your set, the sum remains to be in your set, and you have an additive identity, that is, there is some, there is something in your group that acts like 0, right? An element B such that A plus B is A. And you have an inverse that is some element B for every A so that A plus B is equal to 0. Then you're called a group. Okay, so the first thing a ring has to be is a group, right? So let's think about a clock. This is the best example of rings and groups. So a clock has 12 hours. Let's just designate 12 as 0 for this experiment, right? So what is 11 o'clock plus 3? 12, 1, 2. Okay. So is it the case on the clock, if I were to add on the clock, do all additions, do all sums end up being a number on the clock? Yes. So we're closed over addition on the clock. Is there a number on the clock that if I were to add it to any hour is 0? Which number is that? 12. What's 3 o'clock plus 12? 3 o'clock, right? So you just go all the way around. That's an identity movement. So 12 on the clock acts as 0. That's why I said maybe we can call 12 0 for that reason. Are there additive inverses on the clock? What do I have to add to 6 to get 0? 6, right? Not minus 6, because minus 6 isn't in the set. To 7, we would add 5. Okay, so it seems that a clock is a group if we have defined addition the way that we've defined. Okay, cool. All right, so all of this is basically to demonstrate that this set of polynomials is going to be a ring. So let's think. If I have a set of polynomials, can we add them? Is the addition a polynomial? Is there something that's acting like a 0? Yeah, 0. Is there something that acts as the inverse of a polynomial? Yeah, minus that polynomial. Okay, cool. So it seems that at least the ring of polynomials, bare minimum, is a group because it has closed addition, identity, and a 0. What else do we have to be a ring? Well, you need to be a monoid. That is to say, you have some type of multiplication operator, and that multiplication operator is associative. What is the importance of associativity here? Or really, why do we insist on associativity? Well, one of the reasons is if we didn't use it, we would have to have a billion brackets everywhere, right? Associativity effectively is the rule that says how you bracket this doesn't matter. It's all equivalent. So why don't you just dispense with writing brackets because of this rule, right? So that's, okay. So it won't matter. A times B times C will be the same thing as A times B times C, right? So we won't get all this bracket pollution. And also to be a monoid, you have to have a multiplicative identity, something that behaves as a unit, as a 1. Okay, so let's think back to our clock. Is a clock with 12 hours a monoid? Okay. Is the product associative? Yeah, it seems to be. Do we have multiplicative identity for every element? No. Do we have multiplicative identity for some of them? Which ones? Okay, so 5, for example. So what do I multiply 5 by on a clock to get back to 1? 5, 10, 15, that's 3, 5. Yeah, 5 times 5 is 25, mod 12 is 1. Okay, so on the clock, some of the hours have a multiplicative inverse, but other ones don't. There is nothing that you can multiply 2 by on the clock to get back 1. Yeah.
This slide says that multiplicative identity.
Oh, no, I've jumped ahead to something else. Yeah, thank you. Okay, to be a monoid, yeah, you just have to have multiplicative identity. You have to have something that behaves as a 1. And on the clock, of course, 1 is that unit. Sorry, thank you for that correction. The last thing that we have to be yeah, what I was talking about was fields. I don't know why I'm jumping ahead so much. Sorry, it's that motorcycle is still just driving around in my head. As I said, this is not too important, right? Okay, so the last thing we need to be a ring is we have to have distribution of addition. Distribution of multiplication over addition. So it has to be the case that A times B plus C distributes like this, and B times C times A distributes like this, right? So if you have a set which obeys the group additive rules, which has multiplication, which has a unit, which distributes over addition, then we're a ring. And what I want to say is that the polynomial ring is that, right? It satisfies all of these properties. So we can at least add and multiply using polynomials without sort of producing something outside of that set. So is the trivial set containing 0 a ring? Yes, right? Because there is addition over it, very basic addition. There's an inverse, there's an identity. They just happen to be the same thing in some cases. How about the naturals? Do they form a ring? No, because there's no identity. Oh, yeah, that's wrong. Like no additive inverse, right here. There's obviously an identity. I just went on a lecture about how it has to include 0, right? But this is weird because like you can subtract some things on n, but not all things on n. Like 4 minus 2 is 2, but 2 minus 4 is minus 2. It's like, so one of the directions is actually okay. Same thing will happen with division. 4 divided by 2 is okay. 2 divided by 4 is not. Right? So we got to be more careful about things. And arithmetic on the clock forms a ring, as we just discussed. Okay, 0 divisors. So this is going to be the bane of our existence when working computationally. A 0 divisor is something that is 2 non-zero terms whose product becomes 0, which is bizarre that zeros can sort of appear without inviting 0 to the party. Are there 0 divisors on the clock? Give me a 0 divisor. 3. Why? 3 times 4 is 0. Oh, that's bizarre. 3 is not 0, 4 is not 0, but their product is 0, right? Bad stuff happens when you have these 0 divisors in your system. So the first thing we want to be able to do is sort of like prohibit them, right? So we want to ensure that our ring doesn't have these, and then it will become an integral domain, right? So an integral domain is a non-zero, so like just forget about the trivial ring. An integral domain is a non-zero commutative ring without 0 divisors. All right, so again, groups, that's sets with addition. If you also get multiplication, then you become a ring. If that multiplication doesn't introduce 0 divisors, then you're an integral domain. We're going to keep building from here. Okay, the integers form an integral domain. That should be fairly clear. Otherwise, give me 2 non-zero integers whose product is 0. It's not gonna happen, right? I don't know how we'd prove that. Probably something about their products having to be sort of, the magnitudes have to all be the same, something like that. I wouldn't know. Okay, so what about clock arithmetic? Okay, this does not form a integral domain because 3 times 4 is 12, and 12 is 0 in our interpretation of arithmetic on the clock. How can we fix it on the clock? Yeah, what happens if we made the clock 13 hours or 5 hours? Think about what the problem is here. 12 factors into 3 times 4, and it's 0. So anything that can reproduce that will also be 0. So what we want is a number of hours that doesn't have any prime decomposition, right? Because then there will be no opportunity to make that 0 aside with the 0 itself, right? So if we had a clock with 7 hours on it, no 0 divisors are possible. Okay, and the question is, will our polynomials form this integral domain without 0 divisors? It's a little bit complicated, but it shouldn't be too hard to sort of argue that, hey, if you give me 2 non-zero polynomials, there's no way I'm going to be able to multiply them together so that they become 0. Okay, fields. So we've done addition, I guess subtraction comes for free along with that because it's just sort of inverse addition. We have multiplication, but what about the inverse of multiplication, division? Do we get to divide polynomials? Not necessarily. Can we even divide integers? Kind of, right? We have this long division that we've been using. Okay, so the next thing that we want to sort of talk about is something called a field. And a field is a ring that has division in it, which effectively means a field is a ring where every element is invertible. Okay, so let's think about what it means to be invertible. I know what's happening. I had to buy a new laptop to stop this problem from working, but I don't want to buy a new Maple license. So my Maple is on this computer and there's no way of transferring it. Okay, sorry about that. Next time, I'll bring my other computer next time because I won't need Maple again. Okay, so the rationals clearly form a field, trivially, right? If I say, here's a fraction, a over b, what do you have to multiply that by to get 1? Yeah, just take the reciprocal of that fraction, and then those things will multiply to 1, like provided that your the numerator wasn't 0. We're never going to be able to invert 0 in any of these rings. Okay, so what happens over like the integers? Okay, we can't divide them, right? We can divide 4 by 2, but we can't divide 2 by 4. So wasn't it weird? Didn't you learn division before you learned fractions? How's that possible, right? You're defining an operation which is supposed to be like an inverse operation, which would merit you moving to fraction. So what did they teach you instead? How would you do 2 divided by 4 if you were in grade 3? What would the result of that be? You don't know what a fraction is, but nonetheless, you still learned what that division was. 0 remainder 2, right? Or you learned that 7 divided by 4 was 1 remainder 3, right? So before learning about fractions, you learned about sort of a type of division where you'd produce a quotient and remainder instead. Okay, so we're going to learn how to do that with our polynomials. And you should have done synthetic division back in high school. Yeah, I'll teach you some tricks. There's some things that we never told you that would have trivialized all of that. So do you know when you take f divided by g, that algebraic operation is equivalent to evaluating f at all of the roots of g? So if I asked you to do something like x cubed minus 2x plus 1 divided by x minus 2, all you had to do was evaluate the numerator at 2. That, fact check me on this, right? But this is actually what the geometric interpretation of that algebraic operation is doing. It is, and this is important actually, because none of you said, look, I agree that you can encode algebraic numbers as polynomials, but then how do I use them for arithmetic? So my response to that would have been, oh, division. Division is equivalent to evaluation in this setting, right? Because if you took sort of like x to the 4th and you divided it by x squared minus 2, you're going to get 4, right? Which is evaluating x to the 4th at the square root of 2, right? So we do have an evaluation procedure that comes by way of doing remaindering. And so remaindering is a huge important thing that we're going to learn how to do, right? Because that's evaluation in this. It's very interesting once you learn about all the geometric, like what's happening geometrically while doing all of these algebraic operations. Did they talk to you much about this when you're doing Gaussian elimination? Because like what you're really doing in that setting is moving around the hyperplanes in such a way that none of the roots of the hyperplanes are moving. But the resulting movement is going to actually like isolate those points for you somehow. But you're still manipulating shapes in space by way of doing algebra, which is the thing that enables us to use a computer to sort of talk about topology and stuff like that. So it's very cool. Okay, so here's the division algorithm, which is the one that you learn from elementary school, right? If I give you 2 integers And let's just say B is positive, just so we don't have to talk about uniqueness or anything. I can say there's unique Q in R called the quotient and remainder, satisfying R is less than the absolute value of Q. And we have A is equal to BQ plus R, right? So this A is the numerator, B is the denominator, Q is the quotient, and R is the remainder. So let's just do some Julia now, right? So I have A is 23, I have B is 7, and in Julia, this division operator naturally is giving you remainder, right? So it's not really giving you division. And be careful, because if you do this, which is integer division from Python, which some of you may be used to, what is this in Julia? Fractions, right? So fractions are in the system already, so be careful. This would have been something very hard to pin down, because numerically everything would have been fine if you were doing stuff with fractions. So it's that division symbol. So what is the remainder upon dividing 23 by 7? Or the quotient, actually, in this case? 3. What's the remainder? 2, right? Because 7 goes into 23 3 times, up to 21, and then there's 2 left over. Here's an invariant. I can just say basically A is equivalent to B times Q plus R. We get true. So here's how you could implement such a thing in Julia. We can talk about some of these features. What does this mean here? That we're saying A is this abstract type T. Why do we want to do that? Well, because I don't want to have to write a remainder. What's remainder going to work over, actually? But not only integers, right? Well, at least integers. But in this setting, that means int 128, int 64, int 4, right? Like all of the various ways that the computer itself can represent integers. Is this algorithm or piece of code going to differ for any of those types? Not really, or no, it shouldn't. Right, so this is smart. We want to write one function that's going to be utilized by Julia to do remaindering on any integers, rather than having to write one each. And actually, it's the case that this could work more broadly on a Euclidean domain. Right? This really should be any type that acts as a Euclidean domain. That is to say, any type which has the remainder algorithm in it should be able to use this function. But for us, we'll just stick with integers. But no, we will be doing this for polynomials as well. We'll get a remainder algorithm for polynomials. So here's the algorithm. It's very simple. If A is less than 0, we'll just change it to be it's positive. This is the sort of cute way of doing an if statement. Right? So if this fails, it'll just go to the next term. And if it passes, then this will occur. Otherwise, just return A. Wait, hold on. Oh, sorry. These are 2 if statements. If A is less than 0, then sort of negate it, make it positive. If A is less than B, then return A, right? If like what's 3? Yeah, 3 mod 6 is 3, right? There's nothing to do there. And then otherwise, here's the main routine, where you just remove one of the denominator from the numerator, and you just repeat that, right, until you can't do it anymore. Now, these are all recursive routines. All my 30. Anyone else took 3400 with me here? No. Okay. So when you write a recursive, is everyone familiar with the term recursion? So recursion is just when a function calls itself, and actually using recursion makes a lot of things way more elegant. Okay, and the important thing about recursion is that the input coming in is smaller than the input on the outside. Is it the case that this function calls something smaller than we originally gave it? It gets A and B, and we're calling it with A minus BB. Okay, so certainly that's going to be smaller, and eventually it should descend and hit one of those 2, right? But this is just the simple remainder algorithm as implemented in Julia. So there you go. Let's just check that it's working. Now, we don't use this remainder algorithm, because someone much more smart than us implemented something way faster than it, right? We don't really want these very core functions to be implemented naively, right? Because they're going to be called billions of times. So you better bet there was a lot of energy going into like integer multiplication, for example. You talked a little bit about Karatsuba, and of course changes a little bit every year. Okay, so do use this rem or this modulo operator. Some of you should be familiar with the % sign being the modulo operator. We can just do some more checks here to show that they're all the same. The quotient is effectively identical, except you're getting the quotient instead of the remainder. So there it is implemented. Of course, we have, so how many times does 5 go into 15? 3 times, so 3 is its quotient. How many times does 101 go into 4? 0 many times, so that's why I get 0 here. How many times does 4 go into 125? Well, 31 times plus one remainder. So we can just sort of walk through a bunch of examples and just print in a structured way. Those of you from Python know of the string formatter. So this is a string formatter. If you put a $sign in front of a variable, it's going to dump in the value for that variable and not print out $A literally. So we can just do a little thing here, right, where it says 15 is equal to its quotient times numerator the numerator is equal to the quotient times the denominator plus the remainder in each case, right? So 15 is 3 times 5 plus 0. 4 is 0 times 101 plus 4. 125 is 31 times 4 plus 1, right? So of course in Julia we have the primitive modulo operator and division operator for respectively remainder and quotient, but be careful to not use double slash because that is the what we use for fractions in this system. All right, so if you just check this out here. Right, that's a fraction. This is the fraction 23 sevenths, which corresponds to this float, which of course is not enough precision, right? This is not genuinely the same number as 23 over 7, or maybe it is. If this was a 3 or a 9, then it wouldn't be. I'm not actually sure that's insufficient. It may be exact. But the point is it won't always be. So here's how I like to remember this remainder algorithm. It's kind of like working with improper fractions. Is that a term in Australia? Yeah. Okay. So you have something like 23 sevenths. Like we call this an improper fraction. And to make it a proper fraction, we can break it into 3 plus 2 sevenths. Right. So if you take this expression here and multiply through by 7, you get the expression on the right, which is the statement about the quotient and remainders. Somehow I just remember it better like this. The reason you've seen this before is exactly for this reason, right? You needed to learn how to do polynomial remaindering to do synthetic division in order to do some integrals, right? You had f over g, and the first step was if the degree of f is bigger than the degree of g, you need to do a remainder operator, right? To basically take that improper polynomial fraction and make it a proper one. Right, so we can just see that we have some identities here too. Oops. So how many times does 7 go into 23? 3 times, and there's the fraction. Right, so just be careful about that. And that's the identity that I wrote up there. Okay, cool. Okay, so we have groups, which are sets of elements with addition and zeros and ones. We have rings, which get you multiplication, which also have to have a 0 and a unit, and distribution. And then on top of that, if we have no 0 divisors, then we have something called an integral domain. Right? So just keep that in mind, right? We're adding restrictions to our set to assure that certain operations exist that we're eventually going to implement into the computer. All right, so let's talk more about these clocks. So I call these things residue classes. Somehow people here don't like that. The other term, so when I say residue class, do you know what a congruence class is? Okay, so you can just think congruence class. But what I really mean to say is that I'm collecting, this is really frustrating, but we'll just wait a second. Okay. So we're going to be, we need to work with all of the integers, but we can't. So we're going to use the Chinese remainder theorem to fix that. We're going to talk about that soon. So we're going to now have to sort of discuss what working with some of the integers is going to look like. Okay, so let's work with n many integers, 0 through n minus 1. And we're going to call this a residue class because what this really is all of the numbers necessary to work modulo n. Okay, if I was working on a clock, you need the numbers 0 through 11 only, right? Because something like 17 o'clock is really 5. Okay, so you'd have a class of numbers 5, 17, 39, the next one, which I can't calculate. And that's a class of numbers. And 5 is the standard representative of that set of numbers. And if you take all of the standard representatives for the clock at 0 through 11, that's called a residue class, right? All of the standard generators. So, but that doesn't really matter. It's just sort of notation and nomenclature. Okay, so we want to work mod n. So I can say things like, if I'm on a clock, I have 11 o'clock plus 3 is 2 mod 12, right? So where this triple equal is equivalence, and this mod is effectively the percent sign operator, right? This is fine. This is the remainder of 14 when you divide out 12. That's why we're talking about remainders. Remainders and modulus are effectively the same thing. Why do we need triple equal here and not equal? Like, why do we have what's the difference between equivalence and equality? This is always a little bit funny to talk about, but it is necessary. Well, I'll just ask you this. Is 17 o'clock the same as 5 o'clock? Not really, because it's 17 and not 5. But is it the same time? Yeah, so they're equivalent, but they're not equal, right? So that's why we use this triple equal sign, right? It's sort of a weaker equality. I don't know, I always found that a little bit interesting. Okay, so here's the notation. I'm going to say A is congruent to B mod C. And this is effectively asserting that the remainder of A on division by C is B, right? This is just the more number theory way of working with it, right? So we're going to talk about moduluses, we're going to talk about remainders, but effectively they're synonymous, okay? We have already seen something similar with overflow. You have already been working with modular arithmetic, unbeknownst to you. So think about it like this. I have to hide it down here. Can you see? That's an 8-bit integer. Okay, so you've learned a little bit about what this means. Okay, so what's the largest 8-bit integer? 255, right? Because you have 8 places to put bits. So that's 2 times 2 times 2, 8 times. That's 256 different configurations of those 8 bits. The 0 one is 0. The last one is 256. Okay, so I'm saying you have 2 to the power of 8 minus 3, which is 252. And I'm going to add 4 to that. What's the result? But what is Julia going to say that the result of this is? First of all, what is 252 plus 4? 256. What did you tell me the largest 8-bit number was? 255. What is Julia going to report back? Well, what should it be, right? 1. Unless I said something wrong out loud. This is 2 to the power of 8 minus 3 plus 4, right?
The extra one, the 0 on the 2.
Yeah, if I made this 3, it would be. So I went to the last number. That's an 8-bit number, and I went back 3 from there, and then I went forward 4. Right. So
I think you went all the way and back to 0 with 2 to the power of 8.
I think both interpretations are kind of equivalent. Like, we're just talking about rotating, like, one of us are moving the clock clockwise by 12 hours and the other one's going anti-clockwise by 12 hours. So you wouldn't expect this to be 1, right? That number. Or would you, right? I'm saying this is 252 plus 4, and it says 1. None of you would find that surprising? Oh, am I saying it wrong? Scheiße. What is this? Hold on. 257. Oh, no, sorry. So 256. Oh, sorry, 253. Okay, no wonder all of you are looking at me so confused. I like to say I was only off by 1. So, like, what's the problem? Okay. Anyway, the whole point here is that when you're working with an 8-bit number, you're not really working with addition properly. You're working over the residue class of 256 numbers. You have 0 through 255. So that is to say, if you take 253 and add 4 to it to get 257, you're not going to get 257 back. You're going to get 1 back. because you're working on a clock with 256 hours. So this isn't wrong. This is the correct response for working in that group, right? And the same is going to be true for 128-bit numbers, 256-bit numbers. This is not wrong. You just have to have it's giving you the answer to the arithmetic in a different setting, but it's not wrong, like so to speak. Okay, so there's this thing called the mod. There's also something called the symmetric mod. We're going to be using both, but it doesn't really matter. It's just swapping out the canonical the canonical numbers in the class. So on a clock, we could have 0, 1, 2, 3, all the way up to 11, or we could designate 11 as -1, right? And 10 is -2, 9 is -3, all the way to 6, or maybe 7. I don't know, that you have to cut it in half, and somehow if it doesn't cut in half properly. But the point is, instead of going from instead of going from 0 to 7, we can go from -3 to 0, 0 to 3. So we can get some negative numbers back. And often the case that this is attractive when writing out polynomials, because it's easier to see. If I were to ask you to add like x plus minus x, right? That's much better than asking you to perform that same computation with all positive numbers where you have to know that you're overflowing to some type of 0, right? So we're going to be working with both mod and symmetric mod. So the trick is this. It's very easy to convert between the two. Why is 5 congruent to -2 S mod 7? Because 7 minus 2 is 5. Right, that's how you convert back and forth. It's also very handy to know this, because what is -1 mod 7? So what is 6 squared mod 7? 1, because it's -1 squared. And doing -1 squared is easier than doing 36 mod 7. Right, so that's why it's sometimes more useful to be working in the symmetric mod. So I think that's part of your project actually, is to implement the symmetric mod, but it's quite easy. I've given it to you here. Right, you just have to shift all numbers by n-half, or the quotient of n-half. Right, you're never to use division. If anywhere in your code you generate a float, stop. You've violated symbolic computation by introducing floats. Everything here has to be done with integers. Like the whole thing depends on integers having exact additions and multiplications and stuff of that nature. Okay, so let's just investigate now some of these different groups and rings. Okay, so Z6, the numbers 0 through 5. Is it a group? Well, let's start looking. So if n equals 6, I'm going to generate, what is this called? What's that? Sequence. All right, so it's just a way, or I guess in this case it's called unit range, but this is going to contain all the numbers 0 through 5 inclusive. So I can do a type of list comprehension here. What I'm going to start doing is generating multiplication tables, but like for addition. So this is going to be an addition table, and then we're going to study the properties of the addition table and try to discern some properties of the group. So I'm just going to say, give me x plus y mod n for y from 0 to 5 and for x from 0 to 5. And it's going to give us a matrix, and the matrix is going to look like that. So here's how you read this addition table. Go away. Okay, so this is 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1. So like an arbitrary position here, this would be 0, 1, 2, 3, and this is 3 plus 0, 1, 2. So 3 plus 2 is 5 in this addition table. What does it mean that we can find zeros all the way through here?
So it would be 6, but represented by 0.
That is true, but like, what's the general thing that is true? Like, so about this, we found a 0 in every column. What is the importance of that? Yeah. Every element has an additive inverse. Okay, so this means it's a group, right? Because everything remained in this table. Every element has an additive inverse. What does it mean that this table is symmetric? That is, the matrix is equivalent to its transpose. Yes, the addition operator is abelian or commutative, right? I forgot that the fancier term for commutativity existed, so I'll use abelian now just to sound more fancy. Okay, so the addition table is symmetric. That means we have an abelian operator, a commutative operator. There is an identity element because that row is fixed and that column is fixed. So that is the place where we find the zero. And each column and row has a zero, and thereby each element has an additive inverse. So we can conclude this is a group. Okay, so we're just going to do some extra fun stuff. Who knows what this is going to do? So the dot is doing some type of sort of piecewise operation. Yeah. Yes. Yes, but what's the effect? What is going to come out of this computation? Effectively, tell me where all the zeros are in this matrix, right? And the fact that we can find a single one in each of these columns means that we can conclude that we have additive inverses. We could do something a little bit more fun. This fine first, we're going to, well, let me just put it out. So what this is going to do, it's saying, what is the additive inverse of 0? 0, because it found the first 0 in this column and it was at the 0 point. What is the additive inverse of 1? Well, it's 5, because the first column, we found a non-zero in the 5th place. What is the additive inverse of 2? Well, it's 4, because in this column, which corresponds to addition on 2, there is a 1 in its 4th row, right? So that's what the sort of this operation is doing, which is kind of fun. We're just showing off some of the Julia features. Okay, let's move now from addition to multiplication. So here's the multiplication table for the same setting. We're working with 0 through 5 mod 6. So the first row is multiplying everything by 0. The first column is multiplying everything by 0. Things seem to be sorted there. Is this a field? What would have to be true about this if it was a field? Yes. Oh, so you're saying the fact that zeros are present in the interior of this is indicative that it can't be a field? Yeah, it's true. It's, well, yeah, I think that's true. Well, at least these zeros mean that we have zero divisors in the group, which is bad. But what's the thing that a field definitely needs to have? Every element needs to be invertible. And if every element was invertible, what should we be able to find in every column? A 1. Is there a 1 in every column? Which columns are there ones? And does it make sense? The first row corresponds with which element? 1. Is that invertible? Always. What other element should be invertible? -1. What's -1 in this set? 5. Is there a 1 in the 5th column? Oh, isn't number theory fun? Like, okay, so we're learning. All right, so like we can, if we take finite amounts of integers, like we can form types of groups and rings that have properties. But this one is not that great, because if we choose 6 integers, we don't actually generate a field, and I want a field. Okay, so let's see. Not all the rows contain a 1, which means there are some elements that do not have multiplicative inverses. For example, there is nothing that you can multiply 2 by mod 6 to get 1. 0, 1, 2, look, nothing. We're just going 0, 2, 4, 0, 2, 4. Okay. So again, you can do something. So there's all of the images of 2. And if I do this, it's saying that elements with multiplicative inverse are 1 and 5, and those without multiplicative inverses are the rest. Okay, so we talked about this. Z6 is not a field because, well, for one, if it was, every element would be obligated to have an inverse, and 2 is not invertible. But how about instead of choosing 6, we choose P, where P is a prime? Okay, what happens then? So here's Z5, which is going to give us the numbers 0 through 4. And let's run the same experiments again, right? So n equals 5, Zn is 0 through 4. Here's our multiplication table. The first row is all zeros, okay? That corresponds to multiplying by 0 on the left, let's say. The first column is all zeros. That corresponds to multiplying by zeros on the right. Is it the case that every column has a 1 in it? Does this mean that every element is invertible in this set? does this correspondingly mean that Z5 forms a field? Perfect. Okay, so now we can work with some of the integers in such a way where we're guaranteed to have multiplication and division at our disposal, which is great, because that's going to be important. And the only thing that we have to do is work with prime many numbers. We won't discuss why sort of that works, but we'll never work in a number field of like characteristic 8. So you may hear me say we're going to be working in residue classes of prime characteristic, which means to say there's going to be prime many of them. The characteristic of a ring is how many times you have to multiply an element against itself to get back 0. Right? So if you're working with P, if you multiply anything by P, which effectively is the 0 in that setting, you're going to generate that 0. So again, here's just some information. Elements with multiplicative inverse, all of them. Elements without a multiplicative inverse, 0. So you're not obligated to give an inverse for 0. 0 is always the special one that we leave aside. So just notice every column here has 1. That means every column here is invertible. The third column indicates that the inverse of 3 is 2, and correspondingly 3 times 2 is 1 mod 5. Now, I want you in the back of your head to remember, I'm doing 2 developments here. We're talking about the integers and properties the integers have, but my true intent is to carry this functionality over to polynomials, because my claim is that polynomials is a number system of some type if you have the perspective that they're encoding algebraic numbers. So do you think we're going to be able to make like the polynomial ring a field in an integral domain and stuff like that? And I don't know, we'll keep searching. Okay, so GCDs, who has dealt with the greatest common divisor algorithm? How do you, well, okay, so, 2 questions then. Who knows what a GCD is? What is the GCD of 3 and 12? 3, okay. How do we compute that? Yes, right, like with a computer. Okay, thank you. Formally, what is the method called for computing the GCD? Euclid's algorithm. Okay, and what types of sets give us Euclid's algorithm? Euclidean domains, right, are effectively rings which also have the GCD algorithm, right? We'll have other types of rings which are important, like unique factorization domains is going to be pretty important for our factorization adventure, because there better be a unique way of factoring stuff before we attempt those factorizations. Okay, so you do know of the greatest common divisor. You should know Euclid's algorithm because it's one of the most centrally important algorithms like ever devised. So let's talk about it a little bit more acutely. So the greatest common divisor is like one of the most fundamental operators of the computer algebra system. I actually found a bug in the GCD algorithm in the Maple system, a pretty serious one, which is a feather in my cap because it's like one of the atomic operators, like the whole system itself. I still remember it was the GCD of t and t squared plus t mod 2 was reporting as 1. I spent 3 weeks looking for that, assuming my code was the problem and it was their code was the problem. And my supervisor had no sympathy for me. He said, Paul, you have to expect this sometimes, right? So you are able to blame the product occasionally. You just have to ascend high enough in the ranks of academics, I suppose. Okay, so let's give a statement of it. I give you 2 integers. Both of them can't be 0. One of them can be 0, actually. I'm just going to define what the GCD is, right? The GCD of A and B, the noted GCD A of B, is the GCD when the following 3 things hold. You're familiar with this divisible by, right? So G divides A and G divides B, right? Means G is a common divisor. We want to find the greatest one. So I'm saying, okay, so first of all, G is a common divisor. If we find another divisor, H, then H has to divide G. This is just a way of codifying that G is in fact the largest divisor because any other common divisor has to divide it. And 3, for uniqueness sake, we're just going to specify that GCDs have to be positive because technically, since we're dividing, negative G would also suffice here. So let's just say, look, it's positive. So we're generating unique ones. So for example, the GCD of 6 and 4 is 2. Because 6 is 2 times 3 and 4 is 2 times 2, right? And the largest factor that's shared between them is 2. What about 6 and 0? Well, the reason that we designate 6 and 0 to have the GCD 6 is for this reason. 6 is really 1 times 6, and 0 is like, can be factored any way that you damn well want. So in this setting, I can say, yeah, like 6 is 0 is 0 times 6. I found 6 in both. So that's how we're going to designate it as that. What's the problem if I were to put 2 zeros in here? Is the GCD 1? Is the GCD 2? Is the GCD? Yes, all of those things, right? So you can't, since it's all of them, it doesn't have definition, right? Functions have to give you back one value, can't give you a bunch of values. That's the same reason we can't divide 1 by 0, because 0 goes into 1 once and twice and 3 times and 4 times and 5 times, which is also why it trends to infinity. It's pretty neat. Okay, so let's keep going. So how then do I actually prove that such a thing exists? Right? So this is sort of like what I found myself in my PhD studies. They said, look, there's a value. It's called the GCD, except in my case, it was intersection multiplicity. But imagine we're in Gauss's era, right? I want this value. It's defined like this. Get it for me. How? How would you do it? Huh? Oh, yes. So like, well, what I'm looking for is, well, we just have to tell everyone how it's constructed. And how do you give a construction for something? With an algorithm, right? Some high-level set of instructions that will terminate necessarily on the answer you're looking for. So here it is. Let me mention that in Julia, we do have a GCD algorithm, and it is one of those primitive functions for which tons of energy have gone into writing. Okay, so I'm just going to multiply 5 random numbers together between 1 and 100, and then find their GCD. Okay, pretty fast. I'll try it again. Pretty, right? That should have been different. Geez, I was just getting unlucky. Yeah. Oh, that's. Oh, yes, you're right. 100. Okay. Okay, 45 and 10. Cool. It's happening pretty fast. So these numbers aren't necessarily small. Let's see if we can do. I don't know. This may be a big mistake. Let's double it. Let's just see if it's still fast. Yeah, still fast. Okay, so like not only is there an algorithm, but the algorithm is fast. Because like one way we could have done it is just gone through all of the numbers and done test divisions, but that would have been too slow to be useful for anything. So what Euclid did is provide a construction, but by way of just enumerating a bunch of properties of the GCD itself. And then an instruction set falls out of that, which is kind of cool. So here is a lemma, I think given by Euclid. The GCD has the following properties. The GCD of A and B is the same thing as the GCD of B and A. Furthermore, if you take A and you do sort of this grade school style division to get a quotient and remainder. So suppose that A is equal to B, the quotient, or B, the denominator, times Q, the quotient, plus R. Then the GCD of A and B is equal to the GCD of R and B. So we've replaced A with R, and this is important. Why? Okay, well, we'll look at the algorithm. We'll discuss it again. It's smaller. And when we're defining recursive algorithms, what we really need to happen is ensure that the recursive call is calling something smaller, because eventually we want to hit the smallest thing called the base case, so the function will return. And then finally, the GCD of AB is the same thing as the GCD of A minus BB. Okay, so I'm saying from these 3 properties, I can make an algorithm which is fast, which produces GCDs. Here it is. Right? So if B is 0, return A, right? That's by the definition. The GCD of anything with 0 is anything. Okay, so now at this point, we can assume the 2 inputs are not 0. And I'm just going to combine rule 1 and 2. You give me A and B, I'm going to find R, that's this, and I'm just going to sort of swap the input. Okay, and the input coming in is necessarily going to, is this necessarily smaller than B? What's the largest remainder you can have mod B? B minus 1. So that position necessarily is smaller. Has to be. What's the stopping condition? B0. So I'm saying at every step of this algorithm, B, the input to B is descending monotonically. which means it has to hit 0, which means this is an algorithm which computes the GCD, which is properly an algorithm because it terminates, which is a necessary quality for an algorithm to be an algorithm. Don't forget that part of it, right? An algorithm is an ordered, unambiguous set of instructions that terminates, right? So there it is. So the GCD algorithm, the Euclid's algorithm, is very elegant and small and works very quickly. And this will work on not just numbers, but anything that's a Euclidean domain, which the ring of polynomials is. So we're going to be able to get GCDs of polynomials. Who cares? Well, what did I say GCDs of polynomials are doing? System solving. Okay, so already this brief 2 lines of code are helping us do system solving. All right, so this plus factoring is going to get us a long way. There's going to be some other, well, there's things in here which we're going to have to talk about, like what it means to have this on polynomials, remainders on polynomials, but you know a little bit about that. Okay, so let's just see. I'm just going to run this. I'm saying, okay, what's the GCD between 2 and 2 times 2? Is 2. What's the GCD between 3 times 7 and 6? 3. What's the GCD between 4 and 13? 1, right? Because 13 is prime. That's almost what sort of can define a prime, right? The GCDs of itself and anything else is 1 besides itself. Don't use this one, right? Use the inbuilt ones. Okay, so there is a GCD in base, which is going to be super fast. And it's going to be equivalent to what we just wrote. Like, obviously, like, you shouldn't write things recursively. I'm glad my 3400 student left because that whole class is about me teaching things recursive, but it's kind of wasteful memory-wise. It creates a bunch of recursive stacks. You really want to take something like this and make it an in-place algorithm, but like that's really for our software engineers to worry about. Just know that like a lot of the things that we define in math are done recursively, but then there's some software engineering that we have to do to sort of like do recursion, but not recursively, if that makes any. Did you ever heard like what an in-place? Did you do quicksort at all? Did you talk about in-place quicksort a little bit? It doesn't really matter, right? Just to say the reason that Julia isn't using this code, like what you say, well, isn't that the code? It works. Yeah, but we can write something much faster. And you want to put much more energy into the basics of your system because everything is going to call it. Okay, so we don't actually want to use GCD. We want to use something called the extended Euclidean algorithm, because what the extended Euclidean algorithm gives us are something called Bezout coefficients. And this is, I think, really, this is what Euclid was doing. We don't really care about the GCD. What I care about are these Bezout coefficients, okay? Because these Bezout coefficients allow me to form linear combinations of the input, right? So here, if you give me A and B, it is possible to form a linear combination of A and B so that it is equal to their GCD. Or in other words, if you give me A and B, it is possible to find S and T so that A times S plus B times T is equal to their GCD. Again, I can form a linear combination of the input to equal to the GCD. Why is this important? Well, this is very important. Suppose we're working in a ring. Let's say, yeah, we're working in a ring, and I want to find the inverse of an element in that ring. How do you do it? Okay, so I'm working mod 7. What's the inverse of 5? Well, okay, that's not wrong, right? You just multiply, you just keep adding 5 to itself until you hit 1. There's a couple problems there. When do you stop? You sort of have to start identifying you're in a cycle, right? So I don't know how to do that. So that's one problem. 2, it's wasteful, right? Like even when you do converge on the inverse, it may take forever. So the question is there a better way of finding inverses? Can anyone see where this is going? Okay, my assertion is that we can compute inverses using Bezout coefficients. And the true purpose of Euclid's algorithm, the extended one, is precisely for doing inversion mod residues of prime characteristic. And I'll show you how this is done. Okay, so first of all, just know that you can modify the GCD algorithm to, at the same time as computing the GCD, also compute the Bezo coefficients. We're not going to be overly concerned with that. If you want to find out more, like take a number theory class, but it's not that complicated. Just pick up a number theory textbook and read about it. So I'm just going to go through here. So now, not only are we getting the GCDs, we are getting these Bezo coefficients. So here, so 4 and 12, I can say that 4 times 1 plus 12 times 0 is 4. I can say for 9 and 12 that 9 times -1 plus 12 times 1 is 3. Right, which happens to be the GCD of 9 and 12. For 4 and 13, which is the important one, which is the one I want to study, here, this tells us that 4 times -3 plus 13 times 1 is equal to 1. Okay, can anyone see why this is useful yet? Okay, I think so. Let's see if that aligns with what I'm going to show next. Okay, so just first to let you know, don't use this. It's slow. Okay, use the inbuilt one for which a lot of energy has gone into optimizing. Right, so that would be base.gcdx. X is for extended. And you can see that we're getting the same output in both cases. Right, so if you want more information on the extended Euclidean algorithm, right, remember you can always just query Julia to get information about stuff. Okay, so oh, geez, that put that there. Inversion. So I want to, okay, let's see. Let's go back to here. Let's look at this for a bit. Okay, so I have 4 and I have 13. What happens if I take this whole equation and I take the whole thing mod 13? What happens? So on the left-hand side, we're going to have 4 times -3 plus 13 times 1 mod 13. So what happens to this? Gone, 0. What's on the right-hand side? 1 mod 13. What is the expression now say? 4 times -3 is congruent to 1 mod 13. What did that do? That gave us the inverse of 4 mod 13. Right, so if I want the inverse of 4 mod 13, I just have to get the Bezo coefficients. And the Bezo coefficient on 4 is the inverse. Any questions regarding that? Because this is really cute, right? That this can do it, right? That getting these coefficients actually gives us inversion. Right? And inversion isn't a computationally easy problem, or it shouldn't be. Right? So I'm going to flesh this out more. But again, if we look here and we just ask ourselves, what happens if we take this mod 13? This is gone. And it reports that 4 times -3 is 1 mod 13. And thereby the inverse of 4 is -3. And the inverse of -3 is 4 mod 13. Right? Or -3 is 10. Right? So I'm saying the inverse of 4 is 10 mod 13. Can we confirm that? So I'm saying the inverse of 4 is 10 mod 14. What's 4 times 10? 40. That's like the easy thing on the multiplication table. Mod 13, well, 13 times 3 is 39. 1 left over, that's 1. All right, so we got inversion, which is pretty neat. Okay, so going down to here, let's flesh that out a bit more. So notice the extended Euclidean algorithm computes inverses Zm. This is important, right? So if you give me a non-zero element from a ring of prime characteristic, the extended GCD gives us these Bezo coefficients, right? So A times S plus M times T is equal to GCD of A and M. I'm not sure why this changed to M. I think this has to do with the Chinese remainder theorem. If we take this entire expression mod M, this will disappear. Right, so that's what happened here. And we're left with the GCD of A and M is congruent to A times S mod M. And if we guarantee that this GCD is 1, then the extended Euclidean algorithm is determining inverses. How can I guarantee that the GCD of A and M is going to be 1? Pick a prime M, right? It has to be 1, right? That's the definition of a prime number. Sometimes people say just make sure that M and A is co-prime. That is technically true, but you don't know what A is ahead of time. Right, so just choose a prime, and that's going to work for any that you can be given. So here's an example. So if the question is find the inverse of 5 mod 13, I just say, okay, run the extended Euclidean algorithm on 5 and 13. You're going to get back the basal coefficients 1, -5, and 2. So this is sort of move things around. This is the GCD. This is the basal coefficient on 5, and this is the basal coefficient on 13. So this says that the inverse of 5 mod 13 is -5. Does that make sense? What's -25 mod 13? Someone check on their computer. Well, we can see. What is -5 mod 13? Oh, -5 squared. So it's 25. -25. -12. Okay, those, hold on. Which coefficients are which? Oh, sorry. Because like that has to be the GCD. So they've moved around these somehow. I think this should be the inverse, yeah. So something is going wrong. Okay, let's try remainder. -5 times 5, remainder 13. Oh, -12 is 113. Yeah, sorry, I'm sort of losing it. Okay, great. But that's not what the symmetric mod would report in this case, right? You want that to be 1, right? This is why sort of moving between, like, the standard representatives of your residue class are important, right? Because I'd rather work with 1 than -12. Okay, so there you go. We did genuinely find the inverse. We wrote this function for you called inverse mod, which effectively just pulls out the correct element, right? So if you want to find the inverse of A mod M, you just call this inverse mod, which is in your project. In this case, the inverse of 5 mod 13 is 8. I don't know, something must have got changed. What is A and, sorry. What is A and M here? 5 and 13. How am I hallucinating now? Right? Yeah. Oh, -5 is 8 mod 13. Jesus, Murphy. Right? Yeah, so it's all fine. I just have to make sure that we're like, this is why I probably should have like insisted on reporting everything as a positive in this case, just so I stop getting confused. But these numbers are all the same, right? They're just we have to standardize them somehow. And there's 2 ways of standardizing them, with negatives or without. But 8 is -5, right? So this is all working. Okay, so 5 minutes. What I want to do. Okay. So it's kind of weird because like things got moved around. So I need to discuss. I'm going to leave Chinese remainder theorem for next class, right? Because that's what Yanni wants me to do. What he wanted me to explain to you is why. Have you looked at the project yet? Okay, so some of the polynomial arithmetic functions that you're working with don't return polynomials. What are they returning? Someone already identified this on the EdStem. Okay, if you look at the function in the project that does division, it doesn't return a polynomial. It returns a function. And the function says, give me a prime number, and then I can actually give you the division. So the reason this is the case is that we can only do the remainder algorithm on polynomials if the coefficient ring is a field. Are the integers a field? No, right? So that means I can only do division once you tell me what residue class I'm working in. And that's what the division function is primed to do. It's saying, I've set it up, you give me a prime number, and then I will go ahead and respond to you with the polynomial. And the reason we had to do it is because of Chinese remainder theorem. So what Chinese remainder theorem allows us to do I have the slides still? So we play a game effectively, right? So I have a secret number. That secret number is U, okay? And you are allowed to ask me what the image of U is modulo anything you want. So you can go, what is U mod 7? What is U mod 13? What is U mod 21? You can do that as many times as you want. And the game becomes, can you reconstruct the original number from that information? And the answer is, yes, you can, right? And I'll flesh out that theorem. I'll give you bounds for what the product of m's have to equal to in order to do this. But this is to say, we're going to give you a multiplication algorithm which utilizes Chinese remainder theorem in order to multiply. And that's going to require that you're able to take f times g and ask for results mod 3, mod 7, mod 11, mods. You need to do the same operation for various amounts of prime numbers. So that's why we set up division the way that we did it. We don't want to say, oh, go say it yourself, like assume that we're working mod 7. It's like, well, we can't, because we're going to have to work in many different residue classes, right? We need to be able to look at f mod 3 and mod 5 and mod 7 and mod 11, right? So the best way to do that, okay, I shouldn't say best, a way to do that was to have the division function report back a function which says, give me a prime, and then I will give you back the result. That is, for our uses, that is a good interface. Now, one of the explicit homework problems is for you, do you know what an interface means? You talked a little bit about the interface is effectively how you expect people to utilize the code that you're writing. And at the moment, having division return functions isn't a very neat interface. I don't think users would expect something like that. So we actually asked you to clean up this interface by creating another type called mod p polynomial, which somehow remembers the p that it's supposed to be using and hides that away from the user, right? So, because it would be better to have this sort of automated in the background, right? So that is explicitly one of your tasks. Okay, so what we did today was effectively just talk about the integers a bit, right? And how we can take some of them and still be able to do things like addition, multiplication, and inversion. In fact, if we take a prime many number of integers, then we're guaranteed to be able to do inversion because that forms a field. Not only does it form a field because we have multiplication and inversion, it forms an integral domain because its multiplication never generates zeros that are unexpected. It's also a ring because we have multiplication, which distributes over addition, which has multiplicative zero and multiplicative identity. And it also forms a group because we can add those things and the additions stay within the same field. And that addition also has a zero. What we're going to start doing next class is take all the things we did in this class on integers and do them for polynomials. Because my claim was that a polynomial is just a different way of representing an integer. So I want you to think about how, well, addition you should be able to do. Multiplication you should be able to do. You've done this on paper and pencil. So maybe what I want you to think about is, well, when you're doing your paper and pencil deductions or arithmetic, think about what you're actually doing. Right? Think about if you can actually codify the steps into a generic method for multiplying two things together and see if you can take that to division. So we'll do that next class. And then next week, I will present to you the factoring algorithm, which is incredible. So see you tomorrow for 1 hour. Okay. Oh, bye, chat. Thanks for coming. Sorry about all the technical difficulties. Sorry I ignored you the whole time. Yes, you may.